Our next section is double integrals in non-rectangular regions. Let's think about what that means. So, up to now we know how to calculate an integral when the region of integration A is a rectangle, right? Because then we have very clear limits. X goes between A and B, and Y goes between C and D. But what if the region of integration is some kind of arbitrary region like this? What happens then? So that's what I'm going to explain in this video. So first, let's remember the very important concept that in a rectangular region, you can choose one of two routes. You may first integrate along x and then along y, which is what I'm showing here on the left. Okay, so what I'm showing here is that your integral, your first integral, is the integral along x from a to b of your function xy with respect to x, and this is represented by these green arrows. Yeah, so we first do the integral along x, and this will be a function which depends on y, as you already know. And what we do now is that we do, outside of this integral, we do the integral along y from c to d. Okay, and this makes sense because if this g of y is like this green arrow, which is a function of y, actually let me color it green so that the explanation makes even more sense. So this g of y is simply telling us what's the value of the integral for this green arrow, and it's a function of y because of course when you change y, which y, the y-axis is the vertical axis here, so when you change y from this to this, the integral has changed, so that's why g is a function of y. And now we integrate this, so we integrate the green arrow. It's as if we sweep the green arrow between c and d. So remember that here y equals c, and here on the top y equals d. So we are sweeping this green arrow. Let me draw it. So we are sweeping the green arrow between c and d like this. Yeah. So those are the limits of the inner integral. So the green arrow represents the inner integral, which depends on y, and we are sweeping it between c and d. Okay. So that's why the inner integral, which is a function of y, is integrated between c and d. This was one of the orders of integration. The other possibility was to do the opposite, to do the outside integral in x between a and b, while the inner integral is between c and d. So we first integrate along y, and this creates this green arrow here. So let me draw a green arrow. So this integral obviously depends on where we are, right? So if we move the integration value of x, we can change between this value and this value. Okay, so the result of the inner integration is a function which depends on x. Okay, and it is this function that we now have to integrate between x equals a and x equals b, so that we cover the whole rectangle. That's why the outer integral is between a and b. And we know that both paths give you the same result, right? So this is Fubini's theorem. Now consider what happens in a non-rectangular region. And things now get really interesting, and I think they are beautiful. So let's imagine we have this region here. So what we have to do is we have to choose between two options. We first integrate along the horizontal path, along x, and then along y, which is the case on the left. Or we first integrate along y, along a vertical path, and then along x. Okay, and this is represented again by these green arrows. But now notice what happens. So now the inner integral, if we write the integral inside, is with respect to x, and the integral outside is with respect to y. So let's think about the limits now. So the limits in this case are, you fix a value of y, okay, so fix a value for the outer integral, so assume that y is constant, which means that we are in some horizontal line. And then you find out for this horizontal line what is the starting point and the ending point of the integral in the horizontal direction. Okay, so this means that this green arrow will be shorter, so the limits will be closer together or further apart depending on the value of y. Okay, which means that these limits depend on y. And indeed, what you can do is that you can write the red curve here, which is the left limit of your region, you can write it as x equals a function of y, right? And this function, you can call it a of y. While the limit on the right, which is this limit here, this blue limit here, this is like the upper limit of the inner integral, right? It's the ending point of the green arrow. And this will be another function, which is again a function of y. So this is a function that you can write as x equals some function of y. And this function, we call it b of y. So in this sense, the inner integral goes between a of y and b of y. Okay? And once you have done this inner integration, the result of this integral is a function of y, right? Not only because there is a y inside of the integrand, but also because there is a y in the limits. So everything will depend on y. Okay, so this will be a function of y. So now this function of y, you can integrate it. And this is like sweeping the green arrow from the case at the bottom, where the green arrow is very small, through all the intermediate cases up to the top, which means that now the limits in y are from c to d. Okay, so those will be the limits in y. And these limits have to be constant. Alternatively, we can do it the other way around. And the other way around means that we first integrate along y, and the result will be the same, right? So we first integrate along y, and then we integrate along x. So now this time, what are the limits along y? So we need to write down these limits of the inner integral. So the inner integral represents these arrows. So what are the limits of these arrows? The lower limit of this arrow is this green function here, sorry, this red function here, which we can write as a function y equals c of x, right? This is just a function, remember, these are the two axes, x and y, yeah? So this red line is simply a function y equals c of x, and that will be the lower limit of our inner integral, while the ending limit of the green arrows is this blue function here, which is an equation y equals d of x, okay? It's a different function of x. So it's basically a function in the xy plane. So this will be the limit d of x, and it will be the upper limit of the inner integral. And once this inner integral is done, the result will be a function of x only. It will be some function of x. So this function of x, we can now integrate it along x, okay? So what will be the limits along x? Well, the limit will be from the initial point to the final point, so x equals a up to x equals b. A, b, okay? So just one trick to remember this, and this is very important. Actually, there are two things that are very important here. The first thing is that once you do the inner integral, that's like doing, for example, in this case, the integral in the horizontal direction, because the inner integral is with respect to x. Then the outer integral has only has to worry about the projection of the whole area. It's as if you projected it into the y-axis, which is the remaining axis, okay? So after doing the inner integral, you project the area into the y-axis so that your original area becomes now a fixed length on the y-axis. And those will be the limits for the outside integral, which is with respect to y, okay? So the inner integral has to project the area of integration into the remaining axis, which is the y-axis, because that's the integral of the outside. while in the other case, exactly the opposite is happening. Since we are integrating first along y, yeah, this means that the area of integration, after we do the inner integral, we have to imagine that we project it into the remaining variable, which is x, which is this horizontal axis. So we project this area onto the x-axis, and therefore we get a line that goes from a to b, and that's the limit for the outer integral. Okay, so that's the first important concept, this concept that the inner integral projects the area into the remaining variable. The second important concept is that the limits for the inner integral are of course a function that relates x to y, right? Because they are describing these curves. But it's important to realize that this must be x as a function of y and not y as a function of x. So how can you remember this? So you must always remember that the inner integral needs to get rid of the x. Okay, so the x variable needs to disappear after you do the inner integral, because you need to end up with a function that is g of y that you can then integrate along y. So this inner integral cannot depend on x, which means that you cannot have an x in the lower limit or in the upper limit. So these cannot be functions that include x. These are functions that they are literally x as a function of y. Yeah? So these are functions that include y, not x. And the same but opposite thing happens here. So we want the inner integral to be an integral along y, which means that the result has to be only dependent on x. Okay, we cannot have this integral depending on y. So the result of this inner integral must not depend on y. And therefore the limits, lower limit and upper limit, cannot be a function that includes y. They must be y written in terms of x. So that's a function y equals c of x. Okay? I think this is best illustrated with an example, which is what I'm going to do in the next video.